My name is Ahmed Rashid. Thank you all for joining this presentation. Um, Myself and my colleague Andrew Sego will share this presentation. So I'm only presenting for the next 20 minutes or so. Very briefly, a little bit about myself. I'm an industry director for renewables at Megger. I'm a PhD in electrical engineering, been with Megger 9 years now. I'm based out of Toronto and I sit on several standards committees. Um, my core skill is developing test equipment products. One thing I'm sure a lot of you know about Megger, but just to reiterate, the name Megger is largely known for DC installation testing. It's very common to hear people use this name as a verb. I need to Megger this, could go Megger that. And that makes sense. The company did invent DC installation testing all the way back in the 1889. But throughout that time, since then, Megger has been quite innovative and produced a lot of firsts in the market. For example, in 1923, the very first multimeter tester, the avometer, which could measure amps, volts, and ohms. First time you get, a combination in one unit. And plenty of other firsts in the market. First three-phase relay testers, test sets, and so on. And over all these years, we've um, produced products for several different types of customers, utilities, construction, and transportation, which we'll focus on today, in particular the automotive segment with the changes happening. So my side of the presentation, I'll focus on electric vehicle charge points and the testing required for those. And obviously that's driven by the adoption of electric vehicles. So it's quite clear to see that there's more and more electric vehicles and plug-in hybrid electric vehicles in the roads. And to support that and to support the general government and even economic push for electric vehicles out on the road. For example, here the U.S. has announced a target of having 500,000 public electric vehicle charge points throughout the U.S. by 2030, which is quite an aggressive plan, but it's probably needed in order to make it viable for everyone to have an electric vehicle. And there are similar ambitions across the world in Canada, the UK, and so on. And to further emphasize the need for the infrastructure, the speed at which electric vehicles are being adopted is quite remarkable. So here, this is a chart showing global orders and purchases of electric vehicles and plug-in hybrid electric vehicles. And you can see in 2021 versus 2022 versus the first half of 2023, it's every month is a growth on the month prior, from just 8% in January, 49% growth in February, 52% growth in May, and so on. And if you drill down into North America in particular, the first half of 2023 versus the first half of 2022, increase in electric vehicle and plug-in hybrid electric vehicle sales has jumped 50%. So it's massive growth, and it really needs the infrastructure to support it. Otherwise, you can only just do short journeys and charge at home. So public charge points are a necessity. And this chart here is from the U.S. government's the U.S. government's Department of Energy's one of their websites, and can look and see all the public chargers available. I can see that when I do all types of chargers, all types of connectors, everything, it only spits out 67,623 public charge points, and that includes Canada. So reaching 500,000 is a tall order. Now there are some chargers that are, for example, in hotels, which can be considered as part of the public because you just go into a charge. However, they're not included in here. These need to be just pure public chargers, not on private property in that sense. So if you included those kinds of commercial chargers, then the number is more like 140 to 150,000 chargers across the US and Canada. But just the public chargers that can take funding from federal government, that's all there is at the moment. And that's across all the different types. So you have AC chargers, DC chargers, combination chargers, and the Tesla network as well. Now, there's a massive problem with these charge points in terms of just having a long trip and you need to charge and you come up to it and you see that, like that picture in the lower right hand corner, charger unavailable. The JD Power survey that was done at the beginning of this year found that a little over a fifth of all electric vehicle users have experienced coming up to a public charger and finding that it's not working. And one of the main culprits is a lack of maintenance budgets. When people did these projects, they didn't factor in the maintenance budget for later on. So if there's no maintenance budget, it goes offline. You can't send somebody to go out and repair it or even figure out what's wrong with it. And public charge points, according to the infrastructure bill that was passed in 2021, there's some stipulations against them for them in order to receive the funding and get access to that funding, portion of that 7.5 billion that was approved. They need to be available and working more than 97% of the time annually. And according to JD Power, a fifth of the public chargers do not meet that. And in response to that, the US government allocated around $100 million made available that needs to be tapped into. And according to them, it's only 4% of chargers are unavailable. According to JD Power, it's a lot more than that. But at least there is some funding available for people who work in this industry to tap into that funding and repair some of these chargers and reduce the frustration that a lot of EV users are experiencing at the moment. So, as Megger, as an electrical test equipment manufacturer, what have we got to offer here? So, I would start with our recommendations for testing, because there isn't really a widely established and accepted testing standard at the moment. A lot of standards are being worked on, but there isn't like a set way to do it. So this is a recommendation from us. And it's applicable to all types of charger connections and charging types. So sometimes the terminology can get a little confusing. You hear about mode 1, mode 2, or level 1, level 2 chargers. And it's basically level 1 and level 2 and DC fast charging or level 3. It's just about how much power they can, what's the maximum amount of power they can give you. So the level 1 charger is basically what you find if you just plug in at home with just an adapter from your wall socket. So it's just 110 volts, 120 volts, and it'll take all night, the whole day to charge a Tesla, for example. Level 2 at home is when you put two phases together. So basically, you've got 240 volts, double the voltage, a little more current, and now you can charge a whole car, a whole electric vehicle in maybe 6 hours. But then fast DC charging, which what makes most commercial sense in my opinion, because you want to, if you're running this commercially, you want to charge as many vehicles as quickly as possible so you can make as much money as possible. So that makes sense to go for DC fast charging from a commercial standpoint, and even from a public charging standpoint for throughput of cars. But that's at the level when you can fully charge a car from almost empty to full in less than an hour or 30 minutes or so. So our recommendations is basically three types of testing that needs to be done on charge points. The first and most important is safety. The safety of that charge point. Is it safe for the person to walk up to it, connect to it, and test and charge? The next most important is functionality, which really covers the communication protocol and triggering events between the electric vehicle and the charge point itself. And then lastly, the performance. How good is it supplying as much energy as required or as expected? And is it supplying that power with adequate, acceptable power quality? There's more to it. I'll dig in a little bit deeper into each one of those, but those are the three kind of segments that we recommend when testing electric vehicle supply equipment or EVSEs. So safety testing. The very first thing is making sure that there's no presence of voltage in the frame or in the charge point itself at a point where a user or someone can come and touch it and feel that voltage drop. In a lot of our equipment and equipment from other manufacturers, there's this kind of symbol, and this is a symbol where the user, we use the user as a reference point with a lot of safety in between. You put your thumb or finger on there, and obviously you connect to whatever it is you're testing, in this case, the charge point with PPE on, so just in case there's a hazardous voltage. But then if you touch that, the instrument itself will see if there's a voltage difference between you and the frame and the connection of that unit. And that needs to be the first test before doing anything else, because if there's voltage present, you need to stop, be very careful, and fix what the problem is. The next most important test is the protective earth connection, which is basically a bonding test between the frame and an earth point or a grounding point. That is important because any fault currents, any issues need to be drained or sent away from people touching it. Now, in itself, that protective earth verification is important, but then another layer of safety is the safety tripping device. Could be a GFCI. But in general, those kind of devices would be monitoring the current flowing through the protective earth. And if it rises above a certain amount, like 6 milliamps, for example, then it'll trip. So for safety, you'd be testing that there's no voltage present. And if there's a protective earth and it's well connected, there shouldn't be a voltage present. If there is a fault current in the charge point, but there's no voltage present because there's a good protective earth, then there'll be a flow of earth leakage current through that protective earth. And if the tripping device is not functioning or is not installed properly, then even though there's this higher current flowing through the protective earth, it's not tripping, it's not disconnecting, and raising the flag that there's an issue here. So these are the kind of tests we would recommend, and the most important tests to be done at regular periodic intervals. Now, a lot of charge points have a lot of telemetry within them that is supposed to measure these things and connect through the networks, through the internet, and feedback to a central location about its issues, or at the very least have that up on the display. But even that telemetry it can go wrong over time, or it can not be measuring correctly. You still need to be independently at the site, on site, verify and check on a periodic basis to make sure the telemetry is working correctly. The next functionality test is predominantly a communication protocol test. AC connections have the specific pins that are there just for communication. Combination connectors that have DC and AC would still be using the AC connection for communication, but if it's just a pure DC one, then they could use power line communication, PLC protocol, to do the communication before sending through the full current. A few things to keep in mind that needs to be checked as well is in the communication protocol. The proximity pilot is a very important safety protocol. The proximity pilot is there to communicate between the electric vehicle and the charge point that the vehicle is there and charging is happening, because any interruption to that proximity pilot signal, for safety, charging needs to be disconnected. That's an important safety communication that has its own channel and is there all the time. Then you have the control pilot signal, which then sends all the different other types of communication, such as the state of the vehicle, state of the charger, the maximum current that a vehicle wants, the type of charging required, vented, not vented, and so on. And there's established protocols for that. So as part of our recommendations is to check these signals that they're available and they're responding as expected. When you send signals back, you get the right response. So the functionality of the communication side of things. And then lastly, the performance testing. Now, you would need a load so you can actually draw the energy out. So either that could be an actual discharge tester of some kind, but what I've seen a lot of people do is they do this maintenance with an electric vehicle and they connect their electric vehicle to the charger that they're testing just for a minute or so that current is being drawn out, and then you measure power quality of what is flowing. I anecdotally, and it is just an anecdote, a good friend of mine has a Tesla. He charges it at home, and every once in a while his fuse box in the house trips while he's charging overnight. And he asked Tesla about this, and they said, yeah, it's a known issue with that older generation of the Tesla. And when we looked at it ourselves and took some power quality in there, we saw that the inverter is taking the AC power coming out of his wall, turning it into DC to charge the batteries. That can sometimes produce some high frequency harmonics, which, if they rise to a high enough level, cause the tripping. And the study that I'm referencing here from Hydro-Quebec, they did this on public chargers, and they did find that in some instances, I mean, there's supposed to be filters on these inverters and so on. Even if it's a DC fast DC charger or a level 2 AC charger, you sometimes get a lot of harmonics, like 10 kilohertz and above. And if the magnitude rises, then the total harmonic distortion can cause problems and tripping and disconnections. And to avoid that, when installing, when checking on a regular basis, we recommend doing a power quality check. And I'll just finish off now with just a couple things. Megger, as an electrical test instrument manufacturer, we have 5 core values to our products: safety of the product, safety of the person using the product, the ease of use, the ruggedness of the product, reliability of these products so they don't fail and you don't have to return them all the time for repair, and then the accuracy of those products that they're tested in the real world and they give you values that you can be confident in. With that in mind, There's two products I just wanted to highlight that would do a lot of what I mentioned. One is the EVCC 300 electric vehicle charge point checker. It's an all-in-one device. It does a lot of those checks that I talked about, not every single one, but a lot of them. It got an automated test mode where it goes through each check and each test and gives you either a check mark or an X, or if it's questionable, it gives you that question mark, that red question mark. It's made so that when on site going up to the charge point, you can just plug right in, run the test, and move on to the next. It's a quick check, and that could be done on a periodic basis just to make sure that everything's fine. And then lastly, the MPQ 1000, which is a power quality analyzer, handheld with waveform capture, scope, DMM modes, and it's more than capable of measuring and logging in the quality of the power that is going through during charging. With that, I will end. I will take questions at the end. You can type them in the chat, and I'll hand over to my colleague for the next presentation. Let me see. So my colleague Andy. There we go. And there we go. That should
Thank
be
you,
Andy. Okay. Thank you.
Thank you. And my name is Andrew Sagel, and I am a product manager for Megger. I've worked at the company for over 20 years. I'm an active member of the IEEE, and what my job really entails is to help design new product to fit new applications. And this is not only just working with standards committees to see what the requirements are, but also getting out in the field, working with the people who are doing the work, because the product, any product you make has to not only meet standards requirements, but it has to be easily usable in the field. Otherwise, what's the use? And what I'm going to discuss here is I'm going to talk about some EV batteries. And one of the first things I want to do is just start off discussing lithium-ion batteries. This is a relatively new technology, and I don't know how many people are really familiar with them, and this might give some insight. Now, when we talk about lithium-ion batteries, we're not talking about a single battery. This is an entire family of batteries, all different types that we're looking at here. And lithium-ion batteries, there are many different types. They all tend to work relatively in the same way. You have a negative anode, a positive cathode, and a separator. This is all immersed into an electrolyte. It's a lithium salt and organic solvent. Okay. When discharging, the anode releases lithium ions to the cathode. When charging, lithium ions are released by the cathode and intercalate into the anode. Now, in this process, an SEI layer, or solid electrolyte interface layer, forms on the negative electrode. This is needed. This is electrically insulating the anode. So it is something that's needed for them to work, and it protects the negative electrode. Now, with that in mind, there is a limited rate at which lithium ions can be accepted during charging. The faster the rate of charging, the more lithium ions get deposited. If the maximum rate of the intercalation is exceeded, then what can happen is you get something called lithium plating that occurs. And lithium plating is a buildup of the lithium that can actually pierce the separator and can lead to short circuits and thermal runaways. I'm sure you've all heard in the media about batteries that burst into flames, and this is one of the reasons. So the maximum rate of intercalation of lithium ions in the anode decreases as temperature decreases. Why is this? Well, if you think about how molecules work, the higher the temperature, the faster they move. The lower the temperature, the slower they move. This means they're moving slower. They can only be accepted at a lower rate. This means that the charge rate must be decreased to avoid excessive SEI buildup and potential lithium plating. And to do that, there's a BMS system, or a battery management system, that's built into lithium-ion batteries. These will monitor the voltage, temperature, rate of discharge, and rate of recharge. And they are intended to maintain the battery safety, so you don't get these runaway conditions. And when I spoke about the different types of lithium-ion batteries, I just want to go brief some of the more popular ones, and two in particular for this presentation is NMC, lithium nickel manganese cobalt oxide. That's a mouthful. These are very commonly used in EV batteries, okay? And you can see they have a good calendar life, they're good at low temperatures, and they have good energy density and power density. It means they can store a lot of energy and deliver that energy, okay? Their safety rating is a little low, at about a 2. Another common battery that's used, and a lot by Tesla, is the LFP, lithium iron phosphate. This is probably one of the more common ones we see in other applications. They don't quite have the same amount of energy density and are not as good at low temperatures, but they have a much higher safety rating on them, okay? So when I say safety rating, keep in mind what we're discussing here is actually the ignition point of the electrolyte. These electrolytes in these are flammable, and they ignite at different temperatures. So what this means is a lithium ion phosphate battery, the electrolyte has to get hotter than it would in a nickel manganese cobalt in order to initiate or ignite, I should say. Now, lithium ion batteries degrade both by calendar aging and battery cycling. Okay, both of them lead to aging. Now, as they age, what happens is the SEI buildup gets larger and larger. This reduces the capacity of the battery and is often referred to as fading. As this happens, the internal impedance of that battery rises. Now, many of the lithium-ion technologies that are out there, you're going to see a relatively linear rise in that impedance until you reach about the 60 or 70% of its rated capacity. When it passes that point, what will happen is that impedance will start going up at a more dramatic rate. Okay? And, whoops, come on, there we go. Didn't want to move it first, man. Okay. So let's talk about a couple of failure modes that we can see in lithium-ion batteries. First of all, you can have short circuits that occur. So what causes these short circuits to occur? And to be honest, a lot of times it's physical abuse that will do it. In fact, one of the tests for lithium-ion batteries is a penetration test. When they're developing them, they have to drive something like a nail into them and make sure they don't erupt. Another common failure is component failures. The BMS itself has a lot of electronics on it, and it's intended to keep them safe, but as with any electronics, they can fail. And of course, manufacturing defects. And as I mentioned before, as you get excessive charge rates, you can get lithium plating that can pierce a separator and lead to a thermal runaway situation. Over discharging also can cause problems. When voltages fall below a minimum, anode material dissolves into the electrolyte, and this can also lead to dendrite formation that can pierce separators. Now, the BMS will generally open the battery when a minimum battery voltage is reached in order to protect everything. However, keep in mind that if you have a battery that's sitting on the shelf for a really extended period of time, That BMS isn't operating, so that battery can fall below its minimum and it can create problems. So even with lithium ion batteries, you don't want to leave them sitting on a shelf for real extended periods of time. You do want to charge them up periodically to make sure that they're in good operating condition. And of course, overcharging. We know overcharging can cause problems. This can cause lithium plating, which can create short circuits. And generally, those short circuits generate a lot of heat, which can ignite the electrolyte. And again, the BMS is in there to keep the battery safe, but it's also one of the failure points too, as well. So let's talk about EV batteries now, about operating with them. Now, the typical types of batteries used in EVs are NMC and LFP. They work on a cyclic application. So the BMS, in conjunction with the car's computer, monitors these. It monitors the entire cyclic application. So it's like doing a discharge test on it every time you drive. So it's getting a good idea of what's happening there. Now with an NMC battery, they're very linear. So it's very easy for that for the car to calculate, identify where the end charge will be. LFPs are relatively linear. They tend to slope off a little bit more, but they can still be tracked on the cars, and they do have the higher safety rating. Now, let's talk about EV repairs for a moment. A lot of the EV repairs right now are being done at the dealerships because a lot of them are under warranty, but this will be ending, and we'll be seeing this coming more to the regular auto shops now, outside the dealerships. Now, a lot of times when an EV battery is replaced, they may just replace the entire battery pack. This is an expensive proposition. They are very expensive to do. Increasingly, what's happening is they're actually repairing them by replacing the bad modules within the pack. And GM is also heading this way. They want to expand that and have it capable of having individual modules replaced. This is more economical, and it will save the end user a lot of money, especially when these come out of warranty. So let's talk about reworking an EV battery. What's involved in this? Well, first, you have to jack the car up, and you have to get to the battery. So that's some disassembly. You have to remove the connectors on it. Now you have to drain the coolant out of it, because these are water cooled, so they have to be drained out. Now, as you can see in this image, there's a lift that has to be placed up right against these battery packs, because they're very heavy. The entire thing has to be disassembled and lowered down. After it's disconnected and you lower it down, now you have to open up the entire pack and replace the modules, the bad modules. Now, many times when you're actually doing the computer diagnostic on the car, these cars will identify and tell you this module is bad and this module is bad. To determine that, it's looking at the voltage of the module. Okay? Now, there is a large amount of labor that is done in disassembling this and getting this battery down. So here's a question. Is it beneficial to test the modules before replacement and reassembly? When you measure just the voltage of a battery, that doesn't really tell you everything. It tells you what the voltage is. You can take a battery out of the drawer, measure the voltage, and then go to use it and find out it's dead, even though the voltage read full. Now, if you recall what we talked about earlier, as these age, the SCI layer builds up, which means the impedance increases. So the better thing to do is, before going through all this work, is to measure the impedance of each of these cells along with the voltage and find those outliers and replace them before you go and reassemble this and find out there's another problem. Now, the byte 5 instrument can be used to measure each module in the battery pack. It can measure individual modules up to 200 volts and tell you the impedance of them. The data can then be trended, and you can easily locate these outliers that are in there and replace them before you do this reassembly. This can also be used with hybrid batteries. With hybrid batteries, sometimes you have to take out the back seat, you have to take a section out of the trunk, you have to remove the connectors, and some of them are also water cooled and have to be drained. Some are air cooled, which are a bit easier. You have to remove the pack, open the pack, and replace this bad cell. Now, at present, it's not uncommon practice that a person just replaces all the cells, and this is pretty costly and may not be required. I mean, it's probably worthwhile to test and replace individual cells. This will save on cost and makes repairs on these vehicles more economical, especially for older vehicles where people may not want to pay the entire cost for a new battery. There's also what's referred to as second use batteries. When an EV battery goes bad, now when these are designed, keep in mind, these batteries are greatly underrated when they're put in because of capacitive fading and their warranty. They typically will have capacity left when they're deemed no longer of use for an EV. So they can actually be used in some secondary applications or second life applications. They may be used in energy storage in residential housing. But before this can be done, the entire pack has to be tested. And again, to do this, you want to test each individual module in there and make sure they're balanced and make sure that they are find any outliers to replace before using this. And this is where the byte 5 really does excel at this. And again, we can measure individual modules up to 200 volts DC, and literally it speeds up the whole process. It's just one measurement, you get all your information, and it can save directly to the unit. And you can easily identify them and find problems. And we're the only ones that actually measure up to this high and do the lithium-ion batteries. Pretty much only the byte 5 does it. And with that, I am going to turn it over.
Great, thank you very much. So that was a very interesting, informative webinar. Thank you very much, gentlemen, for presenting that. Now, I was informed that you weren't able to hear me earlier, so just wanted to go over a couple things before we go into the questions section of the webinar. We have some good questions that were put forth into the chat. A little bit about us. We are a national and international distributor. We've been in business for over 20 years now. We have certified thermographers on staff and warehouses all across the country. We are real people, so we definitely take to heart the statement, please, buy from people, not just the internet. We have people here that are ready and happy to help you at any time you need assistance with any of the products that we offer. You can see we cover a lot of industries, including the ones on the left here and many more. It's electric vehicles, of course, that we discussed today, but also R&D, semiconductor, educational, research and development, and so forth. You can see on the right, we have a lot of different products that we carry, including all the products that were referenced in this webinar and many, many more. We've worked on our website and we continue to work on it continually. You can see we have really great filtering results on the left here. So you can filter searches by different criteria to get to what you need right away. And we're always looking to add to this and basically improve it. So all the time we're constantly upgrading and making it easier to use. Now, we do have some great questions I want to put forth to the team. Thank you for submitting these. And the first question that we have that has been submitted is, if the car indicates that there are bad cells, why would we need to test the rest?
Okay, I'll take that one.
Okay.
Is because the amount of labor that you're putting into actually taking this battery pack down, disassembling it, and replacing the bad cells. Again, this is a verification because this is actually going to measure the impedance of the cell. You can have a battery that's showing a good voltage and the impedance still could be bad. That's why you don't want to waste all that time you did and replace them, put it back, and find out you still have a problem. It's not good for business, and it's not good for your end customer to see that. So we want to take that one extra step and just do these measurements, which are very quick to do and could save a lot of time.
Great, thank you very much. That's good to know. Now there was another question that was submitted. There was a slide that showed the results of a test with two cells that read high. Could I compare the results of different EV batteries?
Yes, you can. What you can do is now the Byte 5 has about 16 gig of memory. So you can literally have hundreds, thousands of results in there. And you can bring them up and look at them. Or another way you could do it is you could actually create a configuration file that's based on a particular battery type. And literally, just every time you get that battery, you do these tests, and you can literally trend each one against one another and just see how they are changing. So you can pull one up from the other and really get a good idea of that. And of course, we also do have software online, or so I shouldn't say online, PC software that can literally be customized to do whatever you want as well.
Great, thank you. And speaking of deviations, another question's come through. When doing testing, you're looking for modules that deviate from the average. How far of a deviation would constitute a bad module?
That's a good question. In general terms, from when we're looking at batteries in general, when you look at the average of the pack, if you see modules that are deviating from that average by 30 to say even 30% and definitely 50%, that's a red flag right there.
Right.
They should not be deviating that far. If they are, that's a sign that there is an issue, potential issue with that particular module.
Got it. Great, thank you. 30 to 50%. That is definitely good to know. Another question has come through, are there published charge point testing standards that are readily available?
I can take that one. There are some general standards about it. They tend to just focus on the safety aspect, but like a comprehensive testing standard for charge points, there isn't one. I'm aware of a few that are being worked on, but there isn't any published.
Okay, great, thank you. Now, another question came through about the tools necessary to do this testing. I know you mentioned power quality analyzers, but where can we see a listing of the tools that would be suggested for doing the testing?
There's a few application notes that have been published that kind of show the sequence of tests and the different type of equipment required. But generally, power quality is needed. A good installation multimeter would be good. And obviously you need the kind of adapters and the connectors that go with it. Something like Megger's EVCC 300 takes care of an awful lot of that for you, but you still need to supplement with a few others.
Sure, absolutely. And I'll add we do carry all these tools and then some.
Yes.
The last question that we have here is that you had mentioned that there are aims for 500,000 public charge points by 2030, which sounds like a lot. Is that realistic?
I have no doubt that within the U.S., the ability to get that many up is possible. A lot of people will be working flat out in order to install that many and ensure that they're good. But just looking at it, looking at other countries, smaller countries, and just looking, like for example, Norway. Norway's adoption of electric vehicles is probably the highest in the world. More than 50% of new vehicles sold in Norway are electric vehicles. And the expectation was, and it's the same expectation in the US, that when you have that many electric vehicles, the
Right.
demand on the grid, the demand on charge points is going to grow by a certain proportion. But Norway showed that it didn't. It didn't grow by that much because the vast majority of people are not doing such long trips that they need to charge outside of home. And by eliminating going to a gas station and just charging at home overnight, it takes care of the vast majority of people's needs. So is it realistic? It's possible. It's pretty difficult, but I suspect that we probably don't need all 500,000 if Norway and other countries with high adoption um, are good enough to kind of extrapolate for the U.S.
Great. Thank you. That's good to know. Now, and if there are any additional questions, we certainly would be happy to answer them for you. You can submit them now, or you can, if they come up later after the webinar, you can email us at sales@tequipment.net. We will get those off to you. I do show there's a hand raised, Rick Mendler. I don't know if you had a question, Rick, that we could answer. No? Okay. Well, Rick, absolutely. Like I said, you can certainly submit any questions to us at sales@tequipment.net. We'll be happy to answer them. If anyone would like a PDF copy of the slides used in this presentation, we can certainly provide you with that as well. So, gentlemen, thank you again very much for your time. We definitely appreciate it. And have a great day, everybody.